Hello everyone, I am Dr. Dinesha HE, Assistant Professor of Chemistry. In this session, I will explain about epoxide and crown ethers, which is the chemistry syllabus for third semester. Let us see what are epoxides. Epoxides are cyclic ether which contains a 3 atoms in a ring that approximates an equilateral triangle. The fundamental structure of epoxides contains two carbon atoms which are attached to an oxygen atom. This is the fundamental structure of epoxide. Two carbon atoms which are attached to an oxygen atom. This makes equilateral triangle structure. This is known as generally epoxide or ethylene oxide. Next we will move on to synthesis of epoxide by Darjan's method. This method is also known as Darjan's condensation or glycidic condensation. This method involves reaction of a ketone or aldehyde with an alpha haloester in the presence of a base to give an alpha beta epoxy ester. This ester is also known as glycidic ester. The general equation for this reaction can be shown as below. This is the general equation for Darjan's method of epoxide synthesis. The aldehyde or ketone can be represented as R, C double bond O, R dash. R dash may be alkyl or hydrogen atom. This aldehyde or ketone reacts with alpha halo ester. This is alpha halo ester because the chlorine atom present in the alpha position, this ester is attached to carbon atom. This carbon atom becomes alpha carbon atom. So chlorine atom is attached to the alpha carbon atom. That's why this is known as alpha halo ester. Aldehyde and ketones reacts with alpha halo ester in the presence of a base, sodium ethoxide, to give an alpha beta epoxy ester. This is the alpha beta epoxy ester because this is alpha position and this is beta position. In this alpha and beta position you have epoxy group, that is oxygen atom. Let us see an example of Darjan's condensation. Acetone reacts with ethyl 2-chloro-propanoate in the presence of base sodium ethoxide to give alpha beta epoxy ester. Next we will see the reactions of epoxide. In the reactions of epoxide, the ring opening reactions are very important because epoxides are very reactive towards the ring opening. There are two types of ring opening. One is acid catalyzed ring opening of epoxide and base catalyzed ring opening reactions of epoxides. Let us first see acid catalyzed opening of epoxides. Epoxides reacts with acid H3O plus to form vicinal diol or glycol. In this case, epoxides reacts with acid in acidic medium to give vicinal diol or glycol. This is also an cyclic compound which containing epoxide undergoes ring opening in the presence of mild acidic condition to give vicinal diol. Vicinal diol means the alcohol groups are present adjacent to each other. Epoxides also reacts with water to give ethylene glycol in the presence of acid. Ethylene oxide or epoxide reacts with HCl to form ethylene chlorohydrate. This epoxide also reacts with hydrogen cyanide to give ethylene cyanohydrate, as shown in the equations. Next we will see base catalyzed ring opening of epoxides. Epoxide undergoes ring opening reaction in the presence of base to give vicinal diols. So this is the epoxide. This epoxide reacts with sodium hydroxide to give vicinal diol. The cyclic compound which containing epoxide is also undergoes ring opening reaction with sodium hydroxide or a base to give vicinal diol. Epoxide reacts with ethyl alcohol in the basic medium to give glycol monoethyl ether. Epoxide or ethylene oxide reacts with ammonia to give ethanol amine, which containing OH and NH2 group adjacent to each other. Next we'll move on to crown ethers. Crown ethers are cyclic compounds that consist of several ether groups. Crown ethers are cyclic polyether with 4 or more oxygen atoms separated by 2 or 3 carbon atoms. Crown ethers are oligomers of ethylene oxide or epoxide. Crown ethers having general formula OCH2CH2 n times. These are some examples of crown ether. So as you can see, number of oxygen atom here 6. These 2 oxygen atoms are separated by 2 carbon atoms. In the first example, oxygen atoms are 6, and in the second example, oxygen atoms are 5. In the third example, oxygen atoms are 4. In the last example, there are 8 oxygen atoms separated by 2 carbon atoms each. The term crown refers to the resemblance between the structure of crown ether bound to a cation and a crown sitting on the person's head. This is the crown ether because this crown ether can accommodate a cation, generally metal ions like sodium plus, lithium plus, potassium plus. So this type of cation can accommodate by crown ethers. That's why the name itself given for them as crown ethers. This is the molecular diagram for this particular crown ether. Let us see how to name these crown ethers. Nomenclature of the first number designates the size of ring, how many atoms are present in the ring, and the second number designates number of oxygen atoms in the ring. For example, 18 crown 6 means the first number designates, that is 18 corresponds to the ring size, which includes all carbon and oxygen atoms, and the second number designates the number of oxygen atoms, that is 18 corresponds to total carbon and oxygen atoms, and 6 corresponds to oxygen atom. If sulfur atom is present in the ring as a heteroatom, these are called as thiacrown ethers. If nitrogen atom present in the crown ether, that crown ether is known as azacrown ethers. Let us see some applications of crown ethers. Crown ethers selectively complex with metal ions depending on their size, number of heteroatoms. Crown ethers combines to metal ions like potassium, sodium, lithium, etc. depending on their size. Crown ethers are useful for dissolving ionic substances such as potassium permanganate in organic solvents. As we know that ionic substances are not dissolved in organic solvents, using these crown ethers we can dissolve ionic substances in organic solvents. 12 crown 4 will combine with lithium metal ion, and 18 crown 6 is bonded to potassium ion. These are some applications of ground ethers. The references. Finally, I thank everyone for watching.